Welcome back to Physics 30. This is the second video in MP1.2. So this time we look at time dilation, the interesting effect that happens there. The fact that two simultaneous events to one observer may not be simultaneous to another observer suggests that time, again, is not absolute. It depends what frame of reference you're in. Could it be that time also passes differently in one reference frame than another? Yes, it does. And just what Einstein's theory of relativity predicts, as the following thought experiment shows. So usually the classic thing you talk about when looking at time dilation is a spaceship traveling. One person's in the spaceship and the other is watching from the outside. So we have a view of an observer on the spaceship as shown in part A. So if we have someone in the ship, so let's say this is a bird's eye view of the ship, I suppose. So there's a person standing here. And what I have here is a light source, a mirror, and a receiver. So this person is watching the very quick part, or a very quick event of light flashing here, bouncing off the mirror and reading here. And a certain time will pass by. And if we want, of course, the time there, we would take the total time divided by 2. All right? So both observers have accurate clocks. The person on the spaceship flashes a light and measures the time it takes for the light to travel across the spaceship and return after reflecting off of a mirror. The rays are drawn at a slight angle for clarity in diagram A. So it would just simply be there and back in one line, but we're just showing you that it's there and back, so it's a slight angle here. Okay? So that's all fine and dandy. You'd go this distance and measured in that time, no problem. The observer in figure B, though, observes the same process. So if it was a see-through ship, the person would see the light travel there and back as well. But something interesting happens with this, because this ship is moving to the right. And again, if it's moving at a slower speed, he would see the same thing there and back. But if this ship is traveling really fast, some fraction of the speed of light, he would see the light as it's going across. So imagine it going across like this, but as it's going across, the ship is traveling to the right. So it'd see go there and back. So this person sees this distance covered. This person sees actually these two angle distance covered. So it's almost like the hypotenuse of two triangles. Whereas this person only sees the opposite side. This person would see a hypotenuse path covered really. So to this observer, the spaceship is moving, so the light travels along the diagonal path as shown going across the spaceship, reflecting off the mirror and returning to the center. Although the light travels at the same speed to this observer, i.e. Einstein's second postulate, the speed of light travels the same no matter what, it has to travel a greater distance. Hence the time required as measured by the observer on Earth will be greater. Well, that's interesting. Let's take a look at some calculations here. So let's say, to figure out the speed of light, it's just simply d over t, right? So d over t. And let's say this distance here, I don't know, let's say it's 10 meters there and back. So 10 meters, so 2 times 10, because it's going to go 10 meters, then back 10 meters. And we're looking for time, and we get 3 times 10 to the 8 is our speed of light. So if we arrange this and solve for t, it's going to be 20 divided by 3.0 times 10 to the 8. And the time to go there and back works out to be 6.67 times 10 to the negative 8 seconds. Okay? Really fast. Extremely fast. Okay? Now let's say this person won't see there and back. Again, at most speeds, that person would see there and back, but if this ship is traveling really fast, like close to the speed of light, we would see this effect happening. As the light is moving back and forth, the spaceship is moving. So the light moves with it. So we still have the same speed, 3 times 10 to the 8, but let's say this distance covered here could represent 300 meters. Because if the spaceship is moving fast, it's going to cover a larger distance. And if we rearrange and solve for t, we get 3.00 times 10 to the 8. And that works out to be 1.0 times 10 to the minus 6 seconds. So look at that. -8, -6, this is larger. So the time experienced by the person on the Earth is longer than the time experienced by the person in the moving spaceship. That is quite huge, actually. It doesn't seem like it makes a difference here, but when we're traveling very fast, it makes a profound difference. So here's the interesting part. So although the light travels at the same speed to this observer, it travels a greater distance. Hence, the time required as measured by the observer on Earth will be greater than that measured by the observer on the spaceship. No, using the distances here, it's a fairly easy equation to derive, but it takes about a page worth of work. But what we get is this. So the time experienced by the person on the Earth, time experienced by person on the ship, the speed of the ship, and of course C, the speed of light. So delta T, the time of the moving object as experienced by an outside observer, which is at rest with respect to the moving object. So we call that relativistic time. So the person on the ground, the key word there is this person is at rest with respect to the moving object. And then we have delta T naught or delta T zero, time of moving object as experienced by the observing in the moving object. So that's his proper time that he experiences. And the speed of the spaceship and the speed of light. Now, if you think about this equation for a second, this little part that's on the denominator, v is usually really, really small compared to the speed of light, right? Our everyday objects are really small, so usually this is going to be 1 minus a tiny, tiny number, for all intent and purpose, 0. So we'll get 1 on the bottom, and if we get 1 on the bottom, well, these two times will equal. So in most circumstances, yeah, there's not a huge difference there, right? But if we're moving really fast, things happen. We could get, if I was in fact moving at the speed of light, we get an interesting thing happening here. If I was moving at the speed of light, these two numbers would be identical. 1 minus 1 is 0, and I get a 0 in the denominator. We can't have that, right? That's undefined. So if I'm moving at the speed of light, we get an undefined mathematical answer. And that kind of suggests that, oh, we can't travel at the speed of light. It's impossible. We get an undefined answer. So we can only travel less than the speed of light. So if we take a look at this, since this factor here, I can't have it equal to 1 because that's undefined. It's always going to be less than 1. And we will always see that the time measured by the person on the Earth versus the time that the person on the ship perceives is different. The time on the Earth is bigger. That is, the time interval between the two events, the sending of light and its reception, is greater for the observer on the Earth than it is for the observer on the spaceship. This is a general result of the theory of relativity and is known as time dilation. Time dilation. So we can think of it like this. Clocks moving relative to an observer appear to run slower than those clocks that are at rest. So it appears that time is going by slower for that person on the ship as viewed by someone on Earth. More time passes by for the person on Earth. However, we don't actually think that clocks are somehow broken. Time is actually measured to pass more slowly in any moving reference frame as compared to your own. Now, this remarkable result is an inevitable outcome of the two postulates of the theory of relativity. So the one with inertial frames, the one that light moves at a constant speed. This factor of 1 over the root of 1 minus v squared over c squared is used quite often in relativity. So rather than write that out, sometimes it's just given a symbol. And we use the Greek symbol gamma to simply write that. So of course we have delta t is equal to delta t naught over 1 minus v squared over c squared. Or we could treat that as delta t multiplied by 1 over 1 minus v squared over c squared. And then you can see it's kind of a mishmash. So for simplicity, t naught times gamma, where gamma is equal to that. All right? Now we can see here that this factor Most of the time, it's simply equal to 1, and delta t is equal to delta t naught most of the time. Okay, so I think it's on the next page, I write that down. But at very high speed, so gamma is never less than 1, or sorry, note that gamma, this whole factor here is never less than 1. At normal speeds, it's equal to 1. So there's no difference here. Delta t equals delta t naught. But when we have v values that are big, so if we have this, or 10% the speed of light, 50% the speed of, 99% of the speed of light, that factor becomes huge. So someone on a ship would experience a certain amount of time, and someone on Earth, they would experience time sevenfold, 7 times that. So if that person on the ship experiences 1 year, the person on Earth experiences 7. Okay, we'll stop the video there, and then we'll come back to time dilation.